Hello everyone and welcome to the second part of my Yamaha CS-60 restoration video. I've ordered in some keys, so finally I get to replace the broken key that someone glued back together. So I'm excited about that. And also the synth action on this keyboard, particularly the Velocity, is amazing. And I've always been fascinated with it. It is by far the best velocity sensitive synth action keyboard that I've played on, and much better than the newer keyboards. And mechanically it is completely different. It is very similar to the organs that were produced in the 1970s, and that makes sense because Yamaha made organs before they made synths. So the technology carried over, and particularly with the CS-50 and the CS-60. In the 1970s, there were three types of pressure sensitivity found on keyboards. The first one was the traditional Velocity, and that was based on how the piano keyboard worked. So when you hit the key harder, a hammer would come down and hit the string harder in the piano, so you would get a louder sound. And the second one was based on like the clavichord, and that's what we've known now as aftertouch. So when you struck the key on a clavichord, the hammer would stay on the key. That would become the point at which the string vibrated. So if you pressed the key harder, you could actually change the length of the string. So by pressing the key after you've struck it, you could actually change the pitch and do some sort of vibrato type stuff. And the third type, which what this synthesizer has, was displacement sensitivity, and that was mostly found on firstly mechanical organs, and then it was carried through to electronic organs. And that was based on, it's sort of like the further you press the key, the louder it would be, or the more the pipes would open on a mechanical pipe organ. So it's similar effect that was produced on the electronic organs, like the electones that Yamaha released at that time. And so mechanically it is completely different to the other two types. So I'm going to show you that because I think it is fascinating. It actually uses a light source to detect how far the key has moved. After we look at that, I've got a lot of cleaning to do because I love cleaning old synths. I love getting my synths to the point where I can imagine that I'm just walking into the shop in the year that they were made, in this case in 1977, and just seeing this brand new synth on the shelf and thinking, wow, that's just amazing. I wish I could own that. So that's exciting. And after that, calibration. So there's a lot of calibration to do with this synth, and I will do it step by step, at least as well as I can anyway, to show you that. So let's get to it. Right, so let's start by replacing that broken key. It's not that difficult to get the keys out. You just remove the spring at the rear of the key. So the one I need to replace is a BE. Taking the spring out, you either lift it up from the top, although that can be difficult because the metal from the spring can get stuck in the plastic sometimes. So I find it easier to just pull it down from the bottom and unclip the bottom part. And then once you do that, the key goes all floppy. You can see there. So to get it out from this point, you just lift it up from the rear and pull it towards the back. So that's pretty easy. And putting the new key in, it's just the reverse. You put in the front facing down, and then attach the spring at the back. Okay, great, so all the keys are fixed and there's no more broken ones. There is one more thing though that I want to do with the keyboard before we go into how the Aftertouch works. And that is that I want to even out the spaces between the keys, because if you have a look at the keyboard, some keys have quite a lot of space between them, and other ones are right next to each other. See, some of them actually have quite large spaces in between them. and the other ones are rubbing. You can hear that one scraping against the next key. So there is a way to fix that. As you put the key on, you'll notice that there's a guide pole that the key has to go on top of. And that pole sets where the key sits on the key bed. So you can bend that pole slightly left or right to set the width between the keys. Now the best way to do that is just a few keys at a time, but I'm going to take off all the keys now and just give the key bed a bit of a clean, because the synth is really old and there's probably a lot of dust and things like that on the key bed. And also that will allow me to show you how the contacts work, the key contacts, and also how the Aftertouch works too. Okay, so half the keys have been removed. You can see how dirty it is. Actually, I've already wiped a bit of dirt off. So it needs a good clean. There's three areas that I'd like to show you. Firstly is just the key contacts. This is a pole or a little rod that goes down to a flat metal bar. When you push this rod, it pushes that bar down, and I'll show you from underneath. And then that bar touches a carbon rod, which makes the key contact. These parts here are those posts to align the keys, and Yamaha's done a really great favour for us, and that's every octave they've got a reference post that's wider than the others. So if you count between this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's every D key. So where's the D? Here. So there'll be another one under D. So we put the D keys on, and next to that we'll bend the posts a little bit away from the Ds, and then from the next D we'll go down and we'll set the space between the keys. And the way you do that is just bending this pole slightly one way or slightly the other way. Now the third part here is this amazing Aftertouch mechanism, and you can see how that works by seeing how the key rests at the end of its travel. So at the top of its travel, the spring is pulling it upwards, and you can see the little bar here that's touching underneath, and that stops the key from traveling further up. So that's the upper limit. And the lower limit, when you press the key down, is that it rests on this bar here, which is like it's that displacement bar. So when you press the key down, you can see that bar move. See, it mechanically moves. That bar's on a hinge that sits at about this place here, and so it rotates downwards like that. So if you have a look here at the travel of the key, see that's around about where you first touch the bar, so you can push it down much further than that. So look at that difference. It's there, it's the start. So that's a good 5 millimeters of travel. That's much further than most keyboards that have Aftertouch, so that you get a lot of good feedback from that distance that you're pushing the key down. Alright, let's pull the keyboard up. Now, to get to where the key contacts are, you need to take out this foam cover. This is exactly the same material that they used to make those burger containers out of at McDonald's. Remember those foam container? Oh, you have to be as old as me to remember. But the burgers used to be made out of this stuff, and then they banned it because it had a lot of CFCs, chlorofluorocarbons. Right, so here's the key contacts. You can see that carbon bar here. These are so well made. These look just 100 times better than the equivalent keyboards that we had at the time. I mean, compared to a Pratt Reed keyboard, this is like Rolls Royce. So you can see there's where the bars contact from the other side. So when that rod sticks up on this side, that's the other end of it. So if I push one of them down, you can see that that's what you're pushing from the top. And so then this metal part touches this carbon rod here. And then the wires are connected at the bottom. So there's 12 wires, one for each note, and there's a single wire that connects the rod at the top. So this is for the octave. So there's a separate bar for each octave. You can see the wire for each octave. And then the other part of the matrix is the single wires come out from each note at the bottom. So that's how the key contacts work. And the aftertouch bar, yeah, the exciting bit. Love this. No wonder it's so responsive. Have a look at how far it moves. Isn't that amazing? So you can see the flag, which is here on the end of this big rod. You can see the flag moving in and out of that little slit where the detector and the light bulb is. I'll turn it on. Okay, so the light's on. The bulb or the light source is on this side and the detector is on this side. You can see the big red wires for the photoresistor. And the slit or the flag moves in and out and blocks the light from hitting the detector in this position. And then when we press the keys down, the flag moves out and lets more and more light hit the detector. And that's what creates our control voltage for the aftertouch. So if I move this bar like this, you can see the flag moving in and out until eventually we let all the light through. So that would be the strongest control voltage. If you have a look at it from this side, you get a bit of a better idea. So you can see the flag moving in and out. So even the smallest changes let a little bit of light through. And I find this keyboard's quite sensitive, particularly at the start. Even movements like this give you a variation in control voltage. So that's excellent, that's awesome. Let's have a look at the schematics now. So here's our schematic. There's our light source. There's our keyboard, and connected to the keyboard is our flag that moves in and out between the light source and the light dependent resistor. Now, light dependent resistors, the more light you shine on them, the lower their resistance. So the more we block that light, the higher the resistance. So if we just have a fixed voltage on one end, we get a variable current at the other end by changing the value of this resistor depending on whether or how much we're blocking the light that's coming through. So the easiest way to remember that is that the more light we shine on, the more current gets through. Now, the current is converted to a voltage by this resistor here, which is acting as the load. So we get a voltage drop across that resistor as the current goes to ground. So the more current we put in, the more voltage drop we get across this resistor. Now, the voltage here is just measured by the op-amp and output at a much higher current. So this op-amp is just an impedance converter. So you can see there's no resistor in the feedback loop, so there's no gain here. Then the voltage that's generated, it's just sent to the VCF, the VCA, the VCO sliders that end up giving you the different amounts that the touch response affects other parts of the synthesizer. So it's a very simple circuit. The only thing that could really go wrong, maybe the op-amp could die, or your light bulb could die, or maybe something wrong with this trim pot. Maybe the trim pot becomes disconnected on the circuit board. That could be an issue, especially if it's the ground end, because if we take away the ground, there's nowhere for this current to go besides the op-amp. So we end up creating a sample and hold circuit, and this voltage in this line would end up building up to 15 volts and would have nowhere else to escape, because the input impedance in this op-amp would be very, very high, so that really there's hardly any current that'll escape here to ground. So we need the current to go to ground so that we can get back to zero when the keys are lifted up. As you can see here, it starts at 0. So this trim pot connection to ground is really important. Right, so it's time for a clean. This synth I will do a little bit differently to the other synthesizers, and that's because it's mostly made of wood, including the top panel. So normally what I would do is take out all the pots and the switches and then soak the top panel in warm soapy water and give it a light rub and that kind of stuff. But the water would seep into the wood and that would be a bit of a disaster. So it's best to probably wipe, but we would need to get rid of a lot of the controls just to get into the small spaces to remove the dust. One of the biggest ones is the ribbon controller. There's a big line of dust right underneath it. Also in the preset panel, there's a lot of dust in there. And the sides of these switches, like down the edges, it's hard to see on the video, but there's a lot of dust in the side of those switches. So to get them out, the ribbon controller is not too difficult. There's screws underneath. Once you undo them, I'll show you now. So, screws underneath. Once you undo those screws, those metal plates come out, and they are pulling the ribbon controller down onto the top of the panel. So once we undo those screws, the ribbon controller comes out this way. So it removes up the top. The preset panel is the opposite. Once we remove the screws, it will lower itself away from the panel. So that way it comes out from below. The same with the switches. Another couple of wood screws and they will lower out from below. Then we can get in around the sides and wipe the sides of the switches, clean inside the panel and underneath the ribbon controller. So that will be it for the top panel. Then lots of Tolex, lots of dirty Tolex. So all these fittings will have to come off. I think I'll probably use a brush and some soapy water for the Tolex just to get into the little cracks. And that will be all around the edges, including the back and underneath. After that, it should look a little bit better. I've already, when I took the keys out, I already cleaned each key individually. So they're nice and shiny. So it's just the rest of the case now. Right, so let's get started. So the two metal plates on the right hand side, they slide to the right, and the two that are on the left hand side slide to the left. Yeah. And then you just push the ribbon controller up from the bottom. You can see it moving. So I might undo this wire a little bit, just to give us a little bit more room when we push it up. So you can see the ribbon controller is lifted now. And have a look at that dust around the edges. There's so much. So you just pull it out and you don't have to move it too far. Just get in and wipe the dust. And then on the sides of the felt itself. Oh, that makes so much difference. I can see it already. The black looks a lot blacker. Just a small wipe makes all the difference. I'm just using a damp cloth. So it's not wet, it's just slightly damp. That's made so much difference to the ribbon controller. I can't believe it. It looks so much blacker now. Just try and get in the gratings as much as I can. Look at that dust, that's amazing. And don't forget the felt part that rests just on top of the keys as well. There's a lot of dust that gets on the inside of that as well. So next is just the rocker switches. The screws just come out of the wood and the rocker switch pulls towards you. Like that. So all we need to do is just clean the sides of the switch and then clean the sides of the hole. So the next thing to clean is the memory panel. There's screws all around the edges. There's quite a few, and there's a bolt at the bottom left-hand corner as well. Then this whole memory panel will come out. I'm going to leave the lid open because there's a ball joint at the front and a little lip. And I suspect it's going to be difficult to pull. It might get jammed, so I'm just going to leave that open. Okay, so the screws are out. There's a little bit of maneuvering, but if you pull it slowly towards you while rocking it back and forward, it eventually comes loose. So you can see that it's much easier to get the dust out now. And you can even take the lid off by unscrewing these screws here. And now all that's left is to clean the dust off. It's much easier to get to now. Look at that. Yes. It actually kind of reminds me of that Sputnik synth, that new CS-80 clone. It's almost the same size. That's much better now. Right, so I'm gonna dry it and then put it back together. Right, so the Tolex is next. We need to get all the dust out. There's a lot of dust in the cracks and also in and around the fittings. So these fittings are going to have to come off. These aren't screws, these are bolts. They go right through to the other side, and there's ground wires that are connected to them. That's so that they don't charge up. They're always earthed. There's not a lot of chance that they would charge up anyway because the whole thing's made of wood, but they've done the right thing and connected ground straps to them. So I'm gonna have to get these off and then give the whole case a bit of a scrub without getting water on the wood. So that will be a little bit of a challenge, take a little bit of time. Now there's two screws. There's one that holds the bolt in, and this second screw with the star washer that holds the ground cable in. So after you undo this one, you've still got one more to go. There. Wow, look at that dust. And then a little bit of soapy water and a big brush. This is a similar thing to what I did with the Moog Prodigy, because it had a really rough surface as well. It makes so much difference with the brush and the soap. Much more than just giving it a wipe with the cloth. Like the blacks just really come up now. There's no dirt in there at all. Right, so next I have to clean around the rear and underneath. So I've chosen to take it off its stand and just rest it against the wall, just to make it easier to get in behind. And also I wanted to stand it up on one end so that any of the moisture would drip down rather than going in behind where that top panel folds open. Because there's a little gap here where the hinges are. So I didn't want to get water down in the back there, because unfortunately we can't separate this top folding bit from the boat because there's just too many controls that individually have to be unscrewed. Most modern all modern synthesizers will have all these controls mounted on a circuit board, and once you take the circuit board off, they all come off. But not in this case, they're all individually screwed on with wood screws. So that's just too difficult. And there's big thick wiring looms and all that kind of stuff, so I'm not going to do that. I'll just rest it on its side and I'll clean it with a brush here and try and get in to these cracks as best as I can. And I'm finished! Finally! Gee, it took ages. But look how shiny it is! It's amazing! Especially the Tolex, it's shiny. You can see the reflection in it. And I don't know whether you can see it or not, but the top panel does look a lot shinier than before, and the ribbon controller is definitely a lot blacker. All the knobs look better. Much better than before. Awesome. Alright, so it's time for calibration. Right, so we start with the KAS board, and the first one is the octave ladder adjustment. So what we want to do is get one multimeter lead onto ground, which is the very last wire on the end. And you'll find there's another wire in here, which is labeled TU, which comes from tune, the tune pot. There it is, TU. So we put one of our probes on TU, there. Now that should be exactly 4 volts, and you get that by adjusting the tune pot on the front panel. So as I adjust the tune pot, you'll see this moves. So we get it to 4. Now once that's set, the actual objective is to get pin 13 of IC2 to 125 millivolts. So you count it the normal way along the left or the top. So from 1 to 13. In the layout, it's labeled wrong. It says that this pin is pin 1. That's never the case for ICs. Always the left-hand side top is pin 1. So pin 13 is here. And I've already adjusted the scale to millivolts. So this is 124.9. That's pretty close. Okay, so for this second adjustment, we're adjusting the offset on the output buffer for that octave ladder network. Now, we measure from pin 6 and we adjust on VR3. The objective is to get the input exactly the same as the output. So our input was 125 millivolts, if you remember from the first test. Now, I didn't need to adjust VR1 because it was already fine. Now, the problem is with this test is that the voltage will change depending on what octave you're in. So you need to press the right key first. We want to start at the lowest octave. So if you press the C1 key, that'll put us in our lowest octave. So this value should be 124.9. The manual says 125, but my meter read 124.9 when we did the first test. Now, if you notice, because this is an exponential keyboard, every time I go up an octave, that figure will double. 0.25, 0.5, 1, 2, and should be 4. 4. Yeah, so that's the Yamaha voltage scaling across the keyboard. So let's get it back to the start. We need to press C1. Oh, that's close. That's not too bad. So it would be this VR3 here. There's not much I have to do. Okay, so we've done the octave ladder. Now we need to do the notes. So we just use one note as a reference, C sharp. So we will need to press C sharp 1 on the keyboard, which is the first black key. So press that first. And then we need to measure the 38th pin of IC2. So it's a 40 pin chip, so just count 3 back. So 40, 39, 38. So this one. That should be 132.4. So it's not. I have to adjust a little bit. And the adjustment is VR2, which is here. That one there, VR2. So we adjust VR2. So the pin 38 is 132.4 millivolts. Okay, so next is the Portamento clock adjustment. We're supposed to measure on IC24 pin 6, but there's no way to get underneath the legs of this IC. I mean, we just can't access them. So, using the schematic, this jumper wire here, this second one from the right-hand side, is on pin 6 of IC24. So we can use that one. Turn it on. Now, the Portamento clock. When we've got the slider, so there's two sliders on this panel here. It's the one on the right hand side. So we're pulling it up towards us for 0, so that would be the lowest point. Make sure that's all the way up. Then we measure pin 6, IC24, and it should be 6 kilohertz. So that's nowhere near 6 kilohertz, so that definitely needs adjustment. Right, so it's VR4. Let me get in here, see if we can adjust it. Right, so VR4, and I need 6 kilohertz. Wrong way. I think anywhere near 6 is going to be close enough. So that's fine. Now we then put the slider all the way to the top, so we're pushing it down from this angle. So we should have maximum Portamento now, so the clock is at its slowest. So it's supposed to be 0.006. So that's fine. So if we needed to adjust that one, it would be this one here. But I'm going to leave that how it is. Okay, the last adjustment for the KAS board is the output buffers for the 8 voices. So they're along here. You can see the buffers, and then you've got the trim pots directly in front of them. And where we measure it is K1 to K8, which are wires along this side of the board. So you'll have to look closely to find them. These are the voltages that travel out to the sample and hold board. So they need to be calibrated. So what we do is first we press down C1. So we're looking for that 125 millivolts again. And we use this VR6 for K1, and then we keep going down like that. Okay, so K1 is a little low, so we need to get that to 125, so I'll adjust VR6. Okay, so that's K1 done. So now look for K2, which is just underneath it. And it's still low, so I'll have to adjust each one up to 125. Right, so all 8 are 125 now. So we're done on the KAS board. So next is the sample and hold board. Now you must have the sustain switch set to sustain 2, which is the lowest point. So up would be sustain 1 and down is sustain 2. So it must be on sustain 2. And the reason is sustain 2 has a special function where if we press one key, it actually fills all 8 voice channels with the voltage for that key to make it easier to calibrate. Now, normally, when we're on sustain 1 and when we're playing just about any other synth, if we wanted to fill each of these sample and hold channels for each of the voice cards with a particular pitch, we would need to press the key 8 times to cycle through the 8 voices and refill them all with the voltage for that key. Now the problem is the CS-60, when you're in sustain 1, sort of acts like that, but not really. What it will do if you press this key 8 times, 1, 2, 3, 4, 5, 6, 7, 8, it'll fill the first 7 voice card sample and hold circuits with that voltage, but leave out the 8th. It just reserves it for some reason in case you press more than one key at a time. So the only way you'll fill this one is when you're pressing multiple keys down. So if you're going to calibrate it with the sustain mode in position 1, you will never be able to do this last channel. It's actually the same for these output buffers as well. This is where the voltages come from and they get stored into here. So when we do those buffers, that's why we also need to switch it to sustain mode 2. Now, once we're in sustain mode 2, we just press any key, really any key on the keyboard, and that key voltage will be filled into all 8 positions on our sample and hold board. So if we just demonstrate that now, so set it to 20 volts so I can get the full range, and let's do the high C, which is a 4 volt control voltage. So now if I go to any position here, so number 5, 4 volts. Number 8, 4 volts. So let's say I'll get one of the ones in the middle. Will be 1 volt something. Oh no, 0.64, but they'll all be 0.64. Now if we switch to sustain 1, it would be all over the place because it'll start assigning those first 7 voices a different voltage. So if I go along like this, if we're in sustain 2, the last key that I pressed would be filled in all spots on the sample and hold board, but if you have a look now, they will all be different. 0.84, let's choose another one. 2.53, you see how they're all different? Now it's assigned, every key that we've pressed, it's assigned a different channel. And that's how you'd expect it to work, but the problem is we'll never get the 8th one assigned because this synth is weird. So, sustain 2, on, press C1, and now we can measure our reference, our voltages, and it should be that 125 millivolts. So let's put that back here. Yeah, so now we need to adjust this pot, well this trim pot that's next to each test point, so that they're 125. So they're all slightly out. So I'll go ahead and do that now. Okay, let's check how good I was able to do it. So position 1, or sample and hold circuit 1. Number 2. Number 3. 4. 5. 6, 7, 7, close enough, 8. Now, let's test that theory. If we put it into sustain mode 1, and I will press another key 8 times. I don't know, let's say this key. 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll just keep going. 15 times. You watch, I've just assigned that voice to the first 7. Number 8 will still be 125. So let's have a look what voltage we had. We had 188, so that'll be 2, 3, 4, 5, 6, 7. You watch position 8. Still 124. It's nowhere near the others. So it never ever assigns voice 8 when you're only hitting one key. That's odd. Anyway, it's time to move on. Right, so next is the KBC board, which controls the filter slope across the keyboard. There's a couple of calibrations to do on that. It's mostly just calibrating the slider ranges on the front panel. It's the same mostly with the subboard actually. You're calibrating the touch response and the ribbon controller and the way the modulation works. If those things sound good, you don't really need to do this calibration. They just put them within certain ranges that are expected for the synth. But if you use those functions and it sounds good, it is good. So you don't really have to do them. So if you can't get them exactly right, it also doesn't matter. The voice cards are more important, particularly the tuning. A lot of the other calibrations on the voice card are just matching one to the other tone-wise and that kind of stuff. So if you play the keys and you don't notice any voices sounding odd compared to the others, most of the calibrations on the voice card you don't have to do either. I would still make sure that I check the pitch. And last of all, the board with the ring mod on it and the main amplifier. So it's pretty important to do that one. But we will start over here and we'll see how we go. Okay, with this calibration, first we use the low range brilliance slider and we put that all the way up, which is its lowest point, and all the way down, which is its highest. And we just try and get minus 2.76 and plus 2.76 by adjusting that range. The pot adjusts the range at both ends like that. So you just try and get it to plus minus 2.76. And you go from one extreme to the other. When you finish, put it back in the middle and then do it with the other one, which is VR2. Same deal. Okay, so my black cable's on ground. My red cable's on one of the outputs, which is one of the terminals labeled O. It's O1 to O8. One for each of the voices. And we're doing the low range slider first, so that's VR1, which is the one closest to the top of the board. We put the low range keyboard brilliance slider all the way up, so we'll get a negative value. And we need to press the C2 key, which is a key near the lower end of the keyboard where the slider range is most effective. You'll notice if I press C1, we get a different value. If we press C3, we get another different value. So we need to use C2. Now this slider doesn't seem to have the range. I can increase it, but I can't get to 2.76. I can't get anywhere near 3.15. It's the best I can do. Now if we use the, take that low range slider and push it all the way to the bottom, we just get the positive value of approximately the same amount. And it doesn't matter what I do with this slider, it's still not low enough. So I'm just going to leave it in its lowest position. That'll have to do. Now we go to the high range slider, put that all the way up, and we need to press C#5. Where's C#5? Here. And we do the same thing, but with the other pot VR2. Looks like I can get that one a bit lower. No. Okay, now if I pull that slider all the way to the front, which is highest point, we just get the positive value of that number. So we can't do any better than that, that's fine. Okay, so this subboard now presents us with our first calibration problem, and that is when a synth was successful, it was often produced for a longer period of time than the ones that weren't successful. And during that longer period of time, more engineering changes were made to improve things. And so quite often modifications were made to the circuit board and they didn't end up looking the same as when they started. And so the schematics and therefore sometimes the tuning procedures didn't really apply anymore. So the test points I need on this board for the first two tests aren't really there anymore. And also the circuit is a little bit different. So I'm going to do the first calibration a little bit differently to what the manual says, and I'll show you what we need to do first. This first calibration, it's just the offset for this op amp here. So our signal comes in from our ribbon controller into I2, and then we need to set the offset so we don't have a bias introduced here. So we just measure test point 1, which is the output of the op amp, and we adjust this offset so that the input and the output are the same. Now it doesn't really matter what the input and the output are, they just need to be balanced. Now the original calibration in the manual tells you to introduce exactly 2 volts here and calibrate this so exactly 2 volts come out. But all you really need to do is press the ribbon controller on the very right hand side. On mine it's about 2.95 volts, and just calibrate here so you get 2.95 volts out. So we'll do that. The problem is this test point's not here anymore. Some of this circuit's probably different. So I'm taking the output from pin 6 of IC12 and using that as my reference. Okay, so first I need to press the right hand side of the ribbon controller down. This is the lowest voltage you'll get from the ribbon controller. So I press that on and I have a look. I've got minus 2.95 volts. Now, all I've done to match the input and the output is, for the input, I've measured this red wire here called I2. It was positive 2.95, and at the outlet of this op amp, I've got negative 2.95, so that's balanced, that's the same. The sign will change from positive to negative because it's an inverting amplifier. So I don't need to do anything on that circuit because I've got the same input to output, so I'm done. Now for the next adjustment, it's exactly the same. Instead of doing an IC12, we're doing an IC13. We're using this balance to get 2.95 volts out of pin 6. Okay, we're on pin 6, IC13. There's our adjustment pot here. We press the ribbon controller down again, and we've got just under 2.92, so we have something to adjust. The third calibration for the ribbon controller is much easier. We just measure TI, this terminal here, which is the white wire, and we adjust this trim pot here so that we get 6.15 volts. So let's do that now. All right, that's pretty close. And number 4, adjust VR15 so the voltage at I1 becomes 9.5 volts. So I1 is this brown wire up here. And we need to adjust that. Let's turn this on so that we get, that's fallen asleep, 9.5 volts. Yes, it's already done. Now, the trim pot we would have had to have used, VR15, is here. So that's the trim pot we would have had to have used if we needed to adjust it. Okay, we're done with the ribbon controller, finally. So we've done these for the slide control adjustment. Next is touch response. And it's the first really funny Japanese English translation. So adjust VR3 when the keys are hardly pressed so that the voltage of TRO, which is number pin 3, which is actually this one down here. You see the brown one? That's TRO. Becomes 6 volts. So we need to hardly press them. Right, so if I hardly press them, I get about 3 volts, 1 volt. Oh, gee, that's all over the place. Depends on how I hardly press them. So I spent a while thinking about this, going, gee, how hard do I actually press them? Is it hardly or is it hard? Now, you read this again. Adjust VR3 when the keys are pressed hard, as in different to hardly pressed, so that the voltage of TRO pin 3 becomes 6 volts. That makes more sense. So if I press them down really, really hard, I get just over 6 volts, so I have something to adjust. And the pot that we use is the one right next to where that wire is. So it's this one here. Okay, I'm pressing the keys hard, and and we're way over 6 volts, and my screwdriver doesn't fit in this pot very well. Ooh, that's close. Come on, go 6. 5.99. 6, yes! Okay, it's done. Right, so next is the pulse width modulation circuit. There's 2 LFOs on this board. One is dedicated to the pulse width and the other one does all the general modulation duties. So the pulse width modulation circuit, we need to calibrate the frequency. Now to do that, we add a voltage into VC1, 5 volts, which sets it at what should be 150 millisecond. Once we set it at that point, we can tell whether it's out or not and then adjust it. So the way we do that is by changing the pulse width modulation speed lever until we get 5 volts into VC1. So I've got the probe on VC1 and the multimeter is on. And so if we just move this pulse width modulation slider until we get to 5 volts, we're at the right spot. So okay, it's way past. That's about as close as I can get it. It's really touchy. Right, now for the real calibration, we put our oscilloscope probe onto the P terminal, which is here, this yellow one. And we have to warm up the old beast. Takes a few minutes. Right, so here's our sine wave for the pulse width modulation. I've marked where the 150 millisecond period is, so we need the tops of the peaks to align with these 2 stickers, which it kind of is, and we need about 3 volts peak to peak, which is about from here to here, so we're slightly under that. So to get the amplitude right, I think that's VR7. No, it's VR8 for the amplitude. So if I adjust VR8, yeah, you can see there's quite a lot of adjustment there. So I get approximately 3 volts peak to peak. So I'm 0.5 volts per division here, so I need to get 3 divisions either side of the center. That's approximately it. And then it's VR7 for the period. I'll just show you that. You can change the period quite a bit. So I think that's approximately where we were. So we're done. Okay, next is the noise generator. So all we do is put the noise lever up full, and then we adjust for 3 volts peak to peak. We measure it number 48 NO, and we use VR10 to adjust. Okay, so there's our noise on the oscilloscope. I'm measuring from this NO, which is a brown wire. It's a shielded brown wire. And there's VR10 here, which we use to adjust the amplitude of the noise. All we have to do is get it between these 2 stickers, which is 3 volts peak to peak. So you can see there's just the smallest touch on that trim pot, and we get a huge difference. So that's approximately right. This noise looks a little bit distorted in my opinion. It shouldn't have these lines here. It's like it's being limited. But that's just the way they've designed the circuit. Okay, so we're up to the last calibration on the sub board. Woohoo! And then we're finished with this board, and then we can do the voice cards. So the oscillator circuit for modulation, we just need to set the period of the waveform for the LFO when the slider's about halfway. So it's similar to what we did with the pulse width modulation circuit. First we need to monitor this VC2. So this pin here, the red one, VC2. And we need to see when that reaches 5 volts by adjusting the speed slider. And all we're really doing is getting the speed slider about halfway. So I've already done that. I've adjusted that slider until I've gotten 5 volts. So we're done. We should be at approximately 150 milliseconds period. And we measure but with our oscilloscope on this yellow wire, which is this SO pin 18. And we're looking for this 150 millisecond period and about 3.2 volts peak to peak, although there's no way to adjust that. We've only really got adjustment over the frequency. So if you see over here on my oscilloscope, I should be for 150 milliseconds, I'm on 20 milliseconds per division, so for 150 milliseconds period I should be about here. But my LFO is running a bit faster, and I'm not going to adjust it because I like fast LFOs. It means that if I put my slider up to full, I'll have a faster speed than normal. And I'll still get the slow speeds when I'm when the slider is near 0, so I'm happy with that. So we're done. We're done with the calibration of everything except the voice cards and the VCA. Now this video has gone for nearly an hour, so what I might do is split off the voice cards into another video, because most people will be interested in the voice cards mainly, so that means they don't have to watch this whole hour. They can just watch that separate video. And also it's getting a bit too much for me to upload. I've got a really slow upload speed. Oh, so it's going to take forever. Anyway, cool. I'm nearly there. I'm so excited. This is one of my favorite old analog polys. And I've done the repair and I've done the clean and I've nearly finished the calibration. Oh, I'm so excited. I can't wait to put it back together. All right, thanks for watching and I'll see you in the next video.